Hi, chemistry. We are going to take our conversion skills and concepts one step further. And I want to extend the concept here and talk about what happens if one of the reactants runs out, right? So we're talking about doing these conversions in the context of a reaction. And so when we're in the context of a reaction, that means that certain things are getting used up, right? And then other things are being produced. So we're going back to this idea of what a reaction is, right? We're taking atoms, we're breaking those bonds, we're reforming the bonds with other atoms. And the thing that we start with is being pulled apart and doesn't exist anymore because the parts of it are being used to reform other things. So we're taking that concept of a reaction and we're mashing it together with this concept of converting things from one unit to another. So this idea of dimensional analysis, using it to convert between different things, can be used to help us understand the context of a reaction. So let's start with the context of a reaction first. If we have two things that we're starting with, let's say we have methane, which is carbons with 4 hydrogens, and that is going to react with oxygen, right? Okay, so if we have this and we react those things together, then the methane is going to combust. The methane's going to burn in the presence of oxygen, and those two things are going to be pulled apart and rearranged to form new things. So the oxygen is going to reform with those hydrogens to create water. The carbon is going to reform with the oxygen to form carbon dioxide. And of course, this would need to be balanced. It's not balanced currently. But this is what our reaction is doing when it proceeds forward. So the question of the day is, what happens if one runs out? What if we have this reaction proceeding forward and we have lots and lots of methane with us? We have a whole truckload of methane, but we run out of oxygen. What happens then? So I bet you can answer that question conceptually, right? What happens then is we have no more oxygen. We have some methane left. We've created some products. And so we can talk about this in terms of a couple vocabulary words. So let me assign a couple vocabulary words to this. First of all, in this case, if it's the oxygen that runs out, the oxygen is called our limiting reactant. Sometimes you'll see this as limiting reagent. So oxygen is going to be our limiting reactant. The thing we have left over in the end, in this case, our methane, that's going to be our excess reactant. And then, of course, over on this side, we have our products. So, big picture, what happens if one of our reactants runs out? Well, our reaction stops. That thing is gone. We can't use it anymore to make more of the product, and our reaction's going to stop. We have made some product, but we also have some of one of our reactants left over. Now, the question that we ask next as chemists would be, well, how much? We know we have no limiting reactant left, but how much product have we made? And how much excess reactant do we have left over? And this is where the dimensional analysis and the conversions from one thing to another thing becoming really useful. Because if we can do these conversions, let's say we know how much limiting reactant we just used, we can use it to convert to the amount of product that we made, or we can use it to convert to the amount of the other reactant that we used. And we can use these things to figure out the answer to these quantitative questions. Okay, as always, let's start with a really basic idea so that we can kind of talk through the concept and wrap our brain around the concept a little bit before we get into the details of the concept or the math behind the concept. All right, so for example, let's say we're making sundaes. And here we see the amount of reactants that we need in order to make the sundae. We need 2 scoops of ice cream plus 1 cherry plus 50 milliliters of chocolate syrup. And if we have that, we have made 1 sundae, right? Okay, so what happens if I walk into the ice cream shop and we start with 8 scoops of ice cream, 6 cherries, and 100 milliliters of chocolate syrup? The question would be, how many sundaes can I make? One of the things is going to run out. And what happens when it does would be the first question, right? So one of these things is going to run out. And you can see here they've kind of done the thinking for you. So we can use 2 sundaes, or we can make 2 sundaes. After we've made 2 sundaes, we have used the 4 scoops of ice cream, 2 for each. We've used a cherry for each, so 2 cherries total, and we've used 50 milliliters of chocolate for each. So we can see right here that our chocolate is going to be our limiting reactant. Our chocolate runs out first. We have made some product. Awesome. We're out of chocolate. And then we have leftover cherries and ice cream. So the cherries and the ice cream would be our excess reactant. Our chocolate's going to be our limiting reactant. And then we have made some product. So this is kind of the idea, right? And we can handle this idea. This is a totally normal idea. We probably deal with this on a regular basis, especially if we're cooking, right? If you're cooking and you run out of sugar, well, you can't make any more cookies. You're going to have flour left over and maybe some chocolate chips and probably some other ingredients, but you're out of sugar. You can't make any more cookies. You've made as many cookies as you can make. So we run into this all the time. We're just going to combine this now to chemistry. This is a really, really important question in chemistry because so much of what chemistry is used for in society is to guide the formation of a product, right? And so we need to know how much of things we need to order so that we don't order too much and things go to waste, or we don't order too much and stuff sits in a warehouse and never gets used, right? We need to be able to figure out how much we need of all these things. It just gets a little bit trickier when you're dealing with things on the atomic level. So before we transition fully into chemistry, I want to revisit this picture just one more time and ask you a question. When we are trying to figure out how much we're going to use of things, and the ice cream and the cherries are a really good example, what unit are we talking in? This might even be a good place to pause and see if you can come up with that answer. So when we're talking about how much ice cream we need to make a sundae, we are talking usually in a counted amount. We're not talking about the mass of cherries we need, right? We're talking about the counted number of cherries we need to make a sundae. And the same is true for ice cream too. We're really not talking about ice cream in terms of a measurement. We're talking about ice cream in a group. 1 scoop, 2 scoops, 3 scoops, 4 scoops. It's a counted number. So when we're talking in terms of chemistry also, this is a really important thing to keep in mind. We're going to talk about what runs out and what's left over in terms of a counted unit. So what is our counted unit that we're talking about? Well, our counted unit is moles. Remember, moles represents a group of particles. So we could use particles as our counted number. That would work, but sometimes those numbers get really bulky. And so instead of using molecules and counting those out, we use groups of molecules or groups of atoms or groups of ions, and we call those groups a mole. So when we're comparing things that run out or are left over, we're going to compare them in a counted amount, which is our mole. And this is convenient for us because when we look at a reaction, right, 2 ice cream plus 1 cherry goes to 2 sundaes. Okay, when we look at a reaction, we talk about the things in that reaction in counted amounts. 2 ice cream scoops, 2 molecules of oxygen, 2 moles of water. Our reaction is already in counted amounts. And so we are going to compare what gets used and what's left over in counted amounts. Now, that's not always the information you have. And so you may have to convert from the information you have, like maybe they give you the mass, into moles, or maybe they give you the volume. You're going to convert into moles before you compare what gets used and what gets left. Okay, so with all of this in mind, let's take a look at an example. We have nitric oxide reacting with oxygen to form nitrogen dioxide. And here's our reaction for it. In one experiment, 0.866 moles of NO is mixed with 0.503 moles of O2. Which one will run out first? Okay, so we're going to try and figure out which one is going to run out first. Now, there's a couple different ways you can do this. When you're dealing with ice cream scoops and cherries, if I just give you a bunch of them, how could you take that information and figure out which one's going to run out first? For example, let's say you have 250 scoops of ice cream and you have 134 cherries. How could you take that information and figure out what runs out first? Pause the video here and think about that. There's really 2 ways you can go about this. You can compare these two to each other. That would be the first way to figure this out. Or you could compare these two to the product. That would be the second way to figure this out. And that's what we're going to do here. Now, there's a number of different ways you can go about this question, but it all kind of boils down to this. Either you need to take these 2 amounts and compare them to each other, or you need to take the 2 amounts and compare them to the product. Okay, so I'm going to go about this question in that second method. I'm going to take the information I have and I'm going to compare them both to my product. So I'm going to take 0.866 moles of NO and I'm going to convert it into moles of NO2. And whichever one can make less NO2 means that one is going to run out first, stop the reaction early, and that one's our limiting reactant. Okay, so pause the video here, see if you can figure that out, and then I'm going to walk you through it. All right, so we are converting from NO into NO2. Whatever unit's on top, I automatically put it on the bottom. And I'm going to go from NO into a different compound. So that means I need to go through the mole hole. And I get this relationship between these 2 things from the balanced equation. So I'm going to look at the coefficients here. 2NO to 2NO2. And I get 0.866 moles of NO2. Now, the trick here is knowing what your answer means. So this answer means if I react all 0.866 moles of NO, that means I have unlimited amounts of oxygen. I can make 0.866 moles of NO2. Now, do I have unlimited amounts of oxygen? I don't. So let's find out how much product I can make if I use all of my oxygen. 0.503 moles of O2. All right, whatever unit's on top, I automatically put that one on the bottom so that I get out of that unit and into the next one. I'm going to convert 2 moles of NO2, and I'm going to use the coefficients from the reaction. So 2 NO2 to 1 O2 gives me 1.006 moles of NO2. All right, so look at these amounts here. If I use all of my NO, I can make 0.866 moles of NO2. If I use all of my oxygen, I can make just over 1 mole of NO2. Now, they give me different answers, right? I can't make both of them. One of them is going to run out first and stop this reaction. Which one's going to run out first and stop the reaction? NO. NO is going to stop the reaction first. And I know that because it stops the reaction when I have made only 0.866 moles of NO2. Oxygen doesn't actually stop this reaction until way later. A lot more moles can be made if I react all of my oxygen and I have unlimited amounts of NO. So I know that NO is going to be my limiting reactant. And when NO runs out, I know how much product I will have made. And I will also know that I'm going to have oxygen left over. So oxygen is going to be my excess reactant. Okay, so that's kind of a brief overview of the whole process and concept. Now, it gets a little bit more complicated than this, and we'll deal with that later on. But for now, I just kind of want you to sit back and soak in this idea, soak in the context, and also notice, let's just come back to this idea that we compared in counted particles. Notice we compared our reactants to our products in terms of moles. Moles are counted amounts. They are groups of a specific number. It's not a measurement. It's not mass. It's not volume. It's a counted amount. So because our reaction up here is listed in counted amounts 2 to 1 to 2, we're also going to compare in counted amounts. So that's why we did this whole thing in moles and we didn't actually try to go to grams or liters or molecules. Okay, so reflect on that a little bit. Think about that. Let me know what questions you have. We will practice this more going forward. I'll see you in class.